Okay, so now that we've established that there's missing energy in every atomic nuclei, we give a special name for this missing mass, and this is called the mass defect. And the mass defect is very simply the difference between the sum of the individual parts, if I add them up and determine that mass, compared to the mass of the actual nucleus once the thing is assembled. And so to do that, the first thing that we need to do is to determine the mass of the nucleus. And there's a little bit of a problem because the periodic table does not give you the nuclear mass. It gives you the atomic mass. But we're not concerned about the mass of the atom. Instead, we're only concerned about the mass of the nucleus. So our first job is to find the mass of the nucleus using the periodic table. So I can get the numbers from the periodic table, and I will have provided a graph for you, or sorry, a condensed version of the periodic table, which gives you the exact mass of particular nuclei that you can use for making your calculations. So make sure that you don't lose that table. Well, the mass of the nucleus is very simple. The mass of the nucleus is equal to the mass of the atom minus the mass of the electrons. Now, we need to add another term in there, and that is how many electrons are in there. So hopefully you remember that the number of protons in an atom is the Z number. And so if we have that same number of protons, then there must be an equal number of electrons. So we can say Z times the mass of the electron. So the atomic number times the mass of the electron, make that calculation and subtract it out of the atom, and what's left is only the mass of the nucleus. So to give you an example, let's take the mass of a helium nucleus. So the mass of the helium nucleus is going to be equal to the mass of the helium atom, which is 4.0266, minus, and in this case the atomic number is 2, times the mass of the electron, 0.005486. And in this case, we find that we have a mass for the nucleus of 4.00156 U's. Now notice all these numbers were in terms of U's. So now that we've established that atomic mass unit number, we're going to continue to make all of our calculations in terms of that unit, that mass unit number. Okay, so this is the mass of the helium nucleus as an example. So let's make sure that we label that. This is for helium. So we have the mass of the helium nucleus. Now let's compare that to the mass of the individual parts. So now to do that, we would need to take 2 protons and add that to 2 neutrons. And in this case, that comes out to be 2 times, and of course the mass of the proton is 1.007276 U's, plus 2 times the mass of the neutron, 1.008665 U's. And when we add that together, we find that the individual masses are 4.032 U's. And you can already see there's a discrepancy. This mass up here is only 2 protons and 2 neutrons, the mass of a helium-4 nuclei. But this is the individual masses of 2 protons and 2 neutrons, and they clearly are not equal to each other. Now, while the difference may seem kind of small, that's a fairly significant portion of the mass is actually missing. We're talking about better than 1%, or about 1% of the mass is gone, is missing. So I added 4 particles together, and I found that on average each one of them was about 1% less massive than it was when they were as individuals. And we'll talk about in just a little bit where that missing mass went to. So in this case, to find our mass defect, we would simply take, and we give a special letter to symbolize this, and that's the lowercase letter delta, and this is simply the total mass of the nucleons. Now by nucleons, we're referring to the individual particles, not when they're combined together. We're thinking of the neutrons and protons as individuals. We multiply their total mass and we subtract them from the mass of the nucleus. So in this case, we get a value of The total mass of the nucleons was 4.0320 U's, and we subtract from that 4 number up here, 4.00156 U's, and this gives us a total mass defect of 0.0304 U's. This is what's referred to as the mass defect. So now, if you notice, I have two equations here. One which is the equation for the mass of the nucleus. This is simply the mass of the atom minus the number of protons, the Z number, times the number of electrons. Remember, the number of electrons will be the same as the number of protons. Then down here I have the same number. If you notice down here at the end of the calculation, I have the mass of the nucleus. And of course, this is the same mass that I got in the calculation up here. So I could actually combine these two equations together to get a longer equation. So let's put a box around this one first. Let's put boxes around each of these equations. Individually, we can make these calculations. But if all I want to know is the value of the mass defect, then I could actually combine the two equations together to get a new equation, which is going to say this. That is that the total mass of nucleons actually, let me rephrase this a little bit. I would like to put this all, let's get rid of these, get rid of the words. So what I'm going to do is I'm going to multiply Z times the mass of the protons. Okay, so this is the atomic number times, which represents the number of protons in the nucleus, times the number of protons, or sorry, the mass of the proton in atomic units, mass units. I'm going to add to that. Now, in this case, I want to get the number of neutrons. So remember, the number of neutrons would be A minus Z. So A includes both the mass of the neutrons and the protons. If I subtract out the Z number, I'm left with only the number of neutrons, and I would then multiply that by the mass of the neutron. Now these two right here combine to give me this, the total mass of the nucleons. What I need to subtract from that is the mass of the nucleus. And the mass of the nucleus, remember, is the mass of the atom minus the mass of the electrons. So in this first portion of the equation, I have the mass of the nucleons, the individual particles, and then in the second portion of the equation, I have the mass of the nucleus once everything is all assembled, of course subtracting out the mass of the electrons. Okay, so let's take a look at an example, and let's use a little more massive nucleus and calculate the mass defect. And remember, we got 0.03 atomic mass units for the helium nuclei. It's a pretty fair chunk of mass missing. Let's see what happens when we use a larger example. So let's take, for example, let's find the mass defect. And this is a calculation you could be asked to do for any atom, is to find the mass defect. So let's find the mass defect for 197, and if you remember, Au is the symbol for gold, and that has an atomic number of 79, or a Z number of 79. Okay, so our first step here is to multiply the total mass of the nucleons. So that is going to be 79 times the mass of the proton. That's 1.00726. That's in terms of U's. I'll leave the units out for right now. I need to add to that 197 minus 79. Excuse me, this will give me the number of neutrons in the gold atom. I need to multiply that by the mass of the protons, 1.08665. Excuse me. Now, from this, I need to subtract, I'm going to put this in brackets, the mass of the atom. Now, it turns out that the mass of a gold atom is 196.0 924. I'm sorry, my mistake. 196.967. And I'll subtract from that the mass of the electrons, so that's going to be 79, the Z number, and the mass of the electrons 0.5486. We'll put the whole thing in brackets. So if you put this into your calculator, you will find that you end up with a much larger mass defect. In this case, we'll end up with a mass defect of approximately 1.67 U's. I'm actually missing the equivalent mass of an entire neutron or proton, depending on which one that I choose. That's a lot of mass missing. So I've added together 197 protons and neutrons, and they have a mass that's only equal to approximately 196 protons and neutrons. So I'm missing the entire mass of a proton and neutron. Now, again, this problem you may be asked to do for any atomic nuclei, and the things that they need to give you is they have to give you the information, the A and the Z number, and on a test, although this is different than the homework, but on a test they would have to give you the atomic mass. Anything else you would be given in your equation sheet. You'd have the mass of the protons, the neutrons, and the electrons. That's given to you. But this information you're not expected to memorize, and of course you're not going to memorize the mass of every atomic nuclei or atom that exists. And so these three pieces of information you'd have to be given in the context of the problem, and they will certainly give them to you, but they will most likely give them to you in terms of atomic mass units. So let's find out what happens to this mass defect. Where did the missing mass go?